Last time we talked about the FH value of different things, but now this time I want to talk about the expectation value. The rotation of the Bloch sphere. Sorry. Now, last time we talked about the expectation value on the X, Y, and Z axis when you apply a magnetic field in the X, Y, and Z direction. Do you remember? What is the expectation value? It's just the projection of the state onto that axis, right? And last time we also talked about the general direction when you apply the magnetic field to it, right? For example, last time we talked about what if I apply the magnetic field in this direction and it's along a vector which is n. Again, the expectation value of the spin is still again the projection to that n. Is that okay? Any questions? So after that, now this time what we are going to do is to study the rotation. So on a Bloch sphere, right, if I want to rotate it about an arbitrary axis, right, so let me just write down. I want to rotate about n. This is given n hat. Just like what we said last time. Last time we only interested in the expectation value, but now I want to rotate about this Bloch sphere. What is the equation that can help us to do the rotation, right? So about the Bloch n for an angle, let's say call it gamma. This is an angle, and assume it is clockwise, right, in the Bloch sphere. Right, so I have this state here, and then you give me an n, any n. For example, if the n is actually pointing vertically, we ask, I want it to rotate by gamma degree about this axis. What should be the equation? Now this one you will learn from quantum mechanics, but I will just give you the result, because the rotation, how to say, the angular momentum is the so-called generator of the rotation. So if you can go through those stuff, then you can derive the equation, but we don't need this in the class. But we sometimes need to be familiar with this equation, because when you do this quantum gate programming, you will see this equation. So I want you to be at least not afraid of this equation. So we will say Rn hat of gamma. It means I'm going to rotate about n, okay, by gamma degree. This is going to be a matrix, a vector, or a scalar. A matrix, because you're rotating a vector, right? So you need to multiply a matrix onto the vector. And this is going to be exponential negative I gamma divided by 2, and then n dot sigma. We have learned, or we have reviewed n dot sigma last time. Now this is very complicated, but don't be scared by this, right? You just need to break it down step by step. You just told me this is a matrix, then this must be a matrix, right? But unfortunately, it's exponential with the parameter as the matrix. So how do we do this? Let's assume we know how to do it first. We will explain more. So you need to do exponential of matrix very often in quantum mechanics, right? So we need to learn that. But let's do it step by step. First of all, what is n? N is the unit vector in an arbitrary direction. It should have 3 components, right? And this is a real space vector. So what are the 3 components that you can have in a real space vector? X, Y, Z. So I'm going to say its x components is nx, ny, and z. Does that make sense? Basically, what I'm saying is, if I have a coordinate here, z, right, x, and then y, this is equals to nx, ny, and nz. It's just a regular 3-dimensional vector. Is it okay? Okay, so this is nx. And what is sigma vector again? What is this poly vector? Do you remember? Exactly. Sigma x, sigma y, sigma z. Again, this can be confusing, but I try to challenge you many times already. It doesn't matter because this is an abstract vector. So now this is actually what? If I look at n is nx, x hat, plus ny, y hat, plus nz, z hat. Correct? That you know very well in a 3-dimensional space. But what is sigma vector? It's just sigma x hat plus sigma y hat plus sigma z hat. Exactly the same form as this one, except that it's coefficient, a matrix. They're the poly matrix. No matter how confusing it is, you accept it because based on linear algebra, they are a valid vector. They are valid. Just a linear algebra, right? They form a vector space. So then what is x hat dot sigma? It's just like usually when you do x dot y or a vector v1 dot v2, what do you get? That is just the inner product, the scalar product, right? All you do is just multiply the corresponding components and add them together. So this is nx, sigma x plus ny, sigma y plus nz, sigma z. Make sense to you for this one? Any questions? Right? And then they are just the matrix. So this one, you go through the math. This is 0. Maybe you tell me so I know that you understand. What is nx sigma x? Maybe you forgot what is sigma x, right? Sigma x is 0, 1, 1, 0. Treat this as an exam. What is nx sigma x? Say again. Pardon. 0, nx, 0, right? So someone tell me what is ny sigma y? Other people. What is ny sigma y? 0, say again. Negative I. Oh, this is y, not z. Yeah. I and y, 0. Very good. Do you guys follow? And then how about sigma c, z, hat? NZ, 0, 0, negative NC. Very good. Yeah. So this one is very common. You can just memorize it. This is just NC, NX plus, no, NX minus I NY, NX plus I NY, and then negative NC. Is this okay? Yeah, a lot of math, but this is the next step, right? I already told you all the basic stuff in the class. And now you need to deal with this if you want to move forward to see more complicated gates that you've checked the IBMQ, all those tutorials, you will see things like that. So this is a rotation. Eventually, what does it mean? It means your rotation, again, why rotation is important? Because it's the gates. Rotation about the Bloch sphere help you to implement the gate. If you know how you rotate, how to get the final state full rotation, then you can use this to construct the gate. Equals to exponential negative I gamma divided by 2 times NC NX minus I NY NX plus I NY negative NC. So that's why it is an exponentiation of matrix. You're going to multiply, this is just a scalar, right? Although it's complex number to each of the term. You are exponentiating a 2 by 2 matrix. Okay, we'll discuss how to do it later, right? But that is what it is. Then let's look at an example. For example, what if n equal to z hat? Okay, what if n equal to z hat? And gamma equals to pi. So what does it mean? It means I have this z hat here, and then I have a state. Maybe this is psi. And I want to rotate it about this guy by pi. And this will bring me to psi dash. Right? It brings me to another state by doing this rotation. But it happened that now n equal to z hat, and then the axis is vertical z. That rotation, right? Is that okay? Okay, so let's try to construct the gate, okay? Then what is sigma, what is n dot sigma in this case? What is this? If n hat equal to z hat. First of all, do you have x and y component? If they don't have, then sigma x and sigma y are not there, right? Because this is just saying that this is equal to 0 x hat plus 0 y hat plus 1 z hat. That's what it's talking about, right? With nx equal to 0, ny equal to 0, and then nc equal to 1. So if you plug in, you will get 1, 0, 0, negative 1, which is just the sigma z, the poly z matrix. That's okay? Now, then how do we do the exponentiation, right? Then I will further just do one more thing. Then I'm going to multiply I, because we need this negative I gamma divided by 2. Let me start a new row. The pen is really not working well today. Let me use this color, right? Then negative I gamma divided by 2 times n dot sigma, right? which is equal to negative I pi divided by 2 times 1, 0, 0, negative 1. Make sense? Which is equal to negative I pi divided by 2, 0, 0, I pi divided by 2. Do you see how I get this? Okay. Okay. So let's start with this, right? I also need to do some evaluation first. So this is 1, you get this. 2, you get n dot sigma. 3, you get this. And then I'm going to do here for 4. I want to evaluate what is exponential of negative I pi dy. Negative I pi divided by 2 0, 0, I. That's wrong. I don't know why it is broken. If I can just use this one. So negative I pi divided by 2, 0, 0, I pi divided by 2. What is this? Do you know? So because it's diagonal, so I can actually write it as exponential negative I pi divided by 2. 0, 0. I am allowed to just take exponential to the element along the diagonal. Okay? So this is exponential. I will prove to you later why I am allowed to do that. I don't know if I want to prove with my pen. There's some. Can I use my hand? My hand may be better. I pi divided by 2. Okay? What is this? What is exponential I pi divided by 2? This I. Exactly. I got lost. Okay? 0, 0. How about I pi divided by 2? Exponential I pi divided by 2. I. Right? This is easy to see because exponential I pi divided by 2 equals to cosine pi divided by 2 plus I sine pi divided by 2, which is equal to I, because cosine pi divided by 2 is what? 0. Sine pi divided by 2 is 1. Okay? Now, so I go through this just to brush up the math. I hope you can do this well in the future. It is your homework. It will appear in your exam maybe. Right? So know how to do the substitution. You don't need to memorize the equation, but you need to know the substitution, right? So then let's think about this. So I'm going to do this. So I am going to apply out instead of n because along z, right? I apply this to a gate. I apply this to a state. I'm going to apply this to the plus state. I just want to give an example. What is this? This is negative I, 0, 0, I, apply to plus state. What is a plus state? In column vector. 1 over square root 2, 1, 1. Everyone can follow? This is the plus state, right? So you just go through the multiplication. I get 1 over square root 2. Because I'm losing space, so I think I will just give you the answer. Otherwise, I cannot fill up. I need to use my finger today. This is just equal to negative I, 1 over square root 2, 1 minus 1. Does it go back to its original place? It's a different state from plus, right? Okay. So let's do one more time. Now I'm going to apply RZ, but 2 times to the plus state. If I apply 2 times, it's just like I'm applying the same matrix, negative I, 0, 0, I. But this time I apply to negative I divided by square root 2, 1, negative 1. Right? Do you see what I'm doing? I applied 2 rotation to the plus state, 2 pi rotation. So it's just like I apply one more to what I had before, because this is 1 pi rotation, right? Is this a 1 pi rotation, right? Now I apply one more. And what do I get here? I actually get this one, negative plus. I get back to the original state after 2 pi rotation. Now some of you say yes, because we don't care about the phase. The only difference is phase. Yeah, you go back to the original state in the original point in the Bloch sphere. But however, for a state, although we say that it doesn't have the physical significance for the global phase, but however, plus is not the same as negative plus as a wave function, right? It does not go back to the original state. After you rotate it by 360 degrees, it does not go back to itself. And that is because you're not really rotating that state in our real space. There is a complicated relationship between the hyperspace and our real space. Because when we are rotating, we are not really rotating a vector in 3D space. We are just that project it to our 3D space, rotate it by pi in the sense by looking at the Bloch sphere, but it does not go back to its original state. Maybe confusing. Let me do one more time, but because of space, I decided to apply 4 times, right? Instead of 3 times, I'm not going to show the 3 times result, and then I'm showing. But I apply it 4 times. Pi to the plus state. Just go through the math. And what do you guess? What will be the result? Apply 4 pi rotation, means 2 pi rotation. Then it will go back to the original state. It turned out to be plus So what does it mean? You need 4 pi rotation to go back to the original state. Right? So that is one thing to show you that the so-called rotation we see in Bloch sphere is not the real rotation that we have, but we just map to the 3D space. The 3D space embedding has some relationship to the hyperspace that the qubit reside. Now I'm going to show you something. Is this possible? How can we have rotation in a 3D space that, how can we have rotation that does not go back to itself after you rotate it by pi? There are many examples. One of this is like that. Imagine this is a coffee cup, right? If I drop it, then the coffee is going to, if I flip it, the water is going to fall out, right? That would be a disaster. Now, if you're just looking at this one, I rotate it by 2 pi, it will go back to its state. But if you consider myself and this one as a whole system, how many times do I need to rotate this one in order to go back to the original state? How many degrees I need to rotate this coffee cup in order to go back to my original state? Now let's take a look, right? So this is pointing to me, right? So I do this, now it's pointing to you, pi. Do more, it's pointing to me, 2 pi, right? But I did not go back to my original state yet, right? Because that was not my original form. So I'm going to rotate one more time. Now point to you, 3 pi. And then now it comes back pointing to me, 4 pi. So after 4 pi, the whole system goes back to the original state, right? So again, 2 pi, and then 4 pi. There are many such examples, and this related to topology. But anyway, the point is that this is just to show you it's possible to have, it's nothing special. The so-called 2 pi rotation in this real space mapped to my system, myself plus this cup is another hyperspace if you want to represent the state of me. And if I want to go back to my original state, I do need to have a 4 pi rotation of this cup in the real space, right? So this is not that important, but it's important, of course, but not important in this class. But I want you to appreciate that a wave function on this Bloch sphere, you need to rotate 4 pi in order to go back to its original state. And this is signified by here, I gamma over 2. Because of this over 2, you need to rotate by 4 pi in order to go back to the original state. And how you came up with this, again, is all quantum mechanics. If you go through the angular momentum of spin, then you will get this equation, right? You can read J.J. Sakura, but there's no need to do that. You just trust that this is the case. Okay, any questions? And another thing is I want you to be able to do this multiplication and exponentiation. Okay? Yeah.
Actually need to do replication.
Yeah. If you want to, no, the math is still correct if you just interested in the qubit without the phase. But if you want to go back to the original wave function, then you need to go back for this amount of rotation, 4 pi.
Let's say one.
Right, yeah. But however, in most cases, if it is just qubit, you don't need to go back to the original phase. Right? It's not necessary. Yeah.
If property in the polynomial. On that thing with that. We just want that.
Actually, I'm not well equipped to answer this. This one, the reason is that because it gives us a group. This related to group theory. It gives you SU. You look at this. I think it's SU special unitary group 2. Yeah. So if you have spin 1, then you actually, unfortunately, then you're 3 by 3 matrix because you can have -1, 0, and 1. Then that will be more profound than this, which I did not study. Yeah. So, but you are right. This is a result of spin half. Yeah. So yeah, we need to study more. I cannot answer now. Okay, then now then let's go to this exponentiation of a matrix. This is a skill. I hope that you learn it, or at least you won't be afraid of it because you always see this exponentiation of matrix. But you apply what we're learning here to other function also, sine, cosine, and log. You will always see something like this. You have operation on the matrix. So in reality, how should we do it? Let me see. I hope that I can write everything here with my finger. Now, how do you exponentiate a matrix? Method 1. If I say exponent alpha m, alpha is just a number and m is the matrix. Okay, what is the exponentiation of this? You just need to go through definition. Do you remember what is the definition of exponentiation? Is summation n equal to 0 to infinity 1 over n factorial, and then the whole thing to the power n. Do you remember this? If you forgot, let me write again. Exponential of x equals to summation n equal to 0 to infinity x to the power n divided by n factorial. Okay, so that is just what, sorry? Yeah, Taylor series. Yes, yeah. Okay, so you can do things like this. Now, if I form in this way, then I know how to do it because this is just what? Matrix multiplication. You go through this matrix multiplication, then you add them back. That will be a matrix also, right? And then you will get the exponentiation. So basically what I try to say is that this is just equal to 1 plus alpha m divided by 1 factorial plus alpha m squared divided by 2 factorial. Just keep adding them to infinity. But it's impossible if you want to do this numerically. Of course, if you converge, you can just do maybe 100 terms or 10 terms. That will be good enough. But this is the fundamental definition. Same for log. If someone asks you to find the log of a matrix, right? In my book, I did talk about a little bit about the entanglement entropy, in which you use the log. You also need to use this method. Okay? Now, but method 2, this is not a general method. Maybe I should not say method 2. Let me just say if m is diagonal. What does it mean? It means I can write m equals to m0, 0, m1, 1, all the way to m and n. And it is 0 elsewhere. It's diagonal. Okay? And that is what I just showed you just now. Just now when I do this Z matrix, I did not do the Taylor series, right? What did I do? I just directly do the exponentiation. But now I want to show you that why it is valid, because it's a good way to practice. So let's start with exponential alpha m. So what for sure is correct is that it is equal to summation n equal to 0 to infinity 1 over n factorial times alpha m to the power n. I just copy this equation. Correct? I just do it. It doesn't matter whether it's diagonal or not. But because it's diagonal, now the good thing is, what is a diagonal element? What happens when it is diagonal matrix when you, when you multiply a diagonal matrix to itself? It is still a diagonal matrix, right? So let's take a look here. For example, let's say I have m. We can do a multiplication, right? M 0 and it is 0, 0. Let me don't use m. Let me just use a, b, c, right? If it's diagonal, I have a 0, 0, b times a 0, 0, b. When you do the matrix multiplication, didn't you see that it is just a squared 0, 0, b squared? Do you see that? Yeah, because this row times this column, and because it's a diagonal, so I just only have a squared. You just keep doing same for larger size of matrix. Okay, so because of this, then you trust me, this is equal to summation n equal to 0 to infinity 1 over n factorial. And I'm going to take out this alpha because alpha is just a number, so it's alpha to the power n. And then because I have capital M to the power n and it's diagonal, I actually have m 0, 0, n. This is not a good notation, n then. Let me change the notation here. Instead of n, right, let's just call it kk maybe. Okay, I have k dimensional. Then what do I get? I get 0, 0 to the power n, m 1, 1 to the power n, all the way to m kk to the power n, and the rest are just 0. I hope you can see it. Right? What I'm trying to say is, because it's diagonal, instead of multiplying the matrix, you can just multiply the elements along the diagonal itself. Right? So capital M to the power n is just equal to each element to the power n. Now, if this is the case, and then now this is summation, and this is just number, I can do them individually, right? Just think about, I have many matrices, each have all diagonal, but now it's just an addition of matrix. So I can make this addition into the elements, because when you add a matrix, you actually add the corresponding element. So this is equal to what? Summation n equal to 0, infinity, alpha n divided by n factorial, m 0, 0, n. Same for other terms. Summation n equal to 0, infinity, alpha n divided by n factorial, m k to the power n, 0, 0. Right? Do you see this? Right? I just multiplied. I need to add all this matrix. So I add from m0, 0 to the power 0 plus m0, 0 to the power 1 with this prefactor, right? Now I just put all this here. But what is this? What is this? Just a Taylor series, exactly. So this one tell me that the whole thing is just equal to exponential of alpha m0, 0 for the element. The rest is 0. And then the last one, Sorry for this, that this is difficult to read. How about green? Exponential alpha mkk to the power, no more power n, right? Exponential mkk. Make sense? Yeah, sorry it's messy, but if you can follow, then should not be messy. If you are listening, ask question, right? I want to force you to ask question, yeah. Which swap gate? Which part? Can you point to me? Which part? Yes, diagonal. Okay. But anyway, I don't expect you to derive this. I just want you to trust me that now, if I have a diagonal matrix, all I need to do is just exponentiate those elements inside. And that's why when I have this rotation about z by pi with this matrix, I dare to just exponentiate these two elements. But remember, do not exponentiate the zero, right? Because based on our proof, it has nothing to do with the zero. Otherwise, you get 1. Okay, this is a mistake I always make at the beginning. So this is a summary of what I said. If you want to exponentiate this, now alpha become negative I gamma divided by 2m. What you can do is just write the Taylor series. That's exactly what I showed you earlier, because this is alpha to the power n, right? Now, what if it is not diagonal? What can you do? Right? You either write the series or you are going to do a transformation. Transform it to the basis that it is diagonalized. Exponentiate it and then go back. Okay? So what you need is you create a U that use this matrix, the new and O, right? The transformation matrix to bring a vector or to go to another, to represent in another basis that we have learned before. But what is this new now? New is where new is the coordinates right? In which M is diagonalized or diagonal. Okay, you try to bring it to the coordinate where it is diagonal. Yeah. U, say again, U is unitary. No, because we are transforming the matrix. Remember, you will use U to in this class, right? U is to transform the vector. And the equation to transform the matrix is U matrix U dagger. Yeah, just that if you will prove it, you will get it. So the first thing, I transform this matrix into a diagonalized matrix, which is difficult. You need to find the eigenvalues. Then I just exponentiate it. It is easy because it's diagonal, right? So I just exponentiate all the diagonal elements. Then I get E. Then I transform it back to the original coordinate. And E to the power m is equal to this one. You are not going to practice this in the class because diagonalization take a lot of effort. We can do that, but a lot of stuff, right? But I want you to memorize this, or in the future when you need to do that, remember to go back. The first mistake we usually make at the beginning when we do matrix exponentiation is that we try to exponentiate all the elements, and we thought that we've done the exponentiation. And this is you always happen in Schroedinger equation, because when you solve Schroedinger equation, you usually have the e to the power Hamiltonian. And how do you exponentiate it? Do not just take individual element. If you really want to do it, diagonalize it, exponentiate it, and then transform it back. And it can be easily done in MATLAB or Python, or even some web page, right? So just don't make that mistake. Okay, and that is what I'm trying to do, although my writing was messy, but now here is a good summary. I want to exponentiate this matrix. It's not diagonal. So what I need to do is either expand in Taylor expansion, okay, or diagonalize it. If it is diagonal, means these two are 0, then all I need to do is, this is the proof, just instead of I'm exponentiating the matrix, I just do e to the power negative I gamma A00 divided by 2. Okay, let me give you a quick example, which I already done before. For example, you want to exponentiate negative I gamma divided by 2 sigma c, because sigma c is diagonal, right? So that is what we are exponentiating, negative I gamma divided by 2, 0, 0, I gamma divided by 2. Because it's diagonal, then the result is, I should not write this, right? The result is exponential negative I gamma divided by 2, 0, 0, exponential I gamma divided by 2. Is that okay? Any questions? Because it's diagonal. Okay, good. So we have learned this skill. Why we want to learn this, right? Okay. So this one, actually I already discussed this. How many degrees do you need to go back to the origin? Let's just look at this one. Exponential minus I gamma divided by 2 n dot sigma. Okay. Now, I showed that earlier, but this time instead of doing the math, right, let's assume like this is difficult to prove, so I only give you an example. Assume n equals to z hat. Okay, then this one will be equals to, because it's z hat, right? I just show you that if it is along the z, then this is diagonal, so this is easy. This is just equal to e to the power negative I gamma divided by 2, which we copy from the previous slide. Is this okay? I'm just copying from here, assuming that we are rotating about that, right? What I need to do is to make this equals to this. If I want to rotate it back to its original state, and then now based on this, what should be the value of gamma? So we basically think that, okay, if that is the case, then we need exponential negative I gamma divided by 2, which is cosine negative I gamma divided by 2, not I, right? Cosine gamma divided by 2 minus I sine gamma divided by 2. I want this equals to 1. Right? I need to make this 1. I need to choose a gamma so that this equals to 1. If this equals to 1, it means I don't have imaginary part. How can I get not getting imaginary part? Well, gamma equal to 0 has no imaginary part. But there's no rotation. Of course, if I don't rotate, it's equal to myself, 1. Then what else? pi. But pi then make this one become 1, right? Then you have I. So you need 2 pi. Correct? But if you make this 2 pi, what is the number here? Cosine 2 pi divided by 2. That's 1. Still not equal to 1. Then the next one must be 4 pi. Right? 3 pi, again, you make this one not equal to 0. Right? So you find that the smallest number is gamma equals to 4 pi. Okay? And that is all because of this 2. If we don't have this 2, then we don't have this problem. And I actually forgot, but what I remember is because of spin half, you get this 1 over 2. Yeah. So I can be wrong, but so a lot of math, right? You need to do it in your homework, but the most important thing, I don't think you need to memorize. I want you to put in your cheat sheet, know the equation. At least if I ask you to say rotate about the Bloch sphere, but how that much of angle, how do you find it? How to find the gates, corresponding gates. But most importantly, I want you to memorize that on Bloch sphere, you rotate by 4 pi, then you will get to your original state. And that is another proof that Bloch sphere is not the real space that the qubit reside. Okay, so actually some people may draw it as 2 spheres. When you rotate, it will go to another sphere and then come back. Then 4 pi will bring you back. That's another transformation. Right, that's one thing. Another thing is about exponentiation of matrix. I make a lot of mistakes like this because if you try to do this, you will get wrong results. Try to do exponentiate of a matrix by just putting in the element. Remember to diagonalize it if it is not diagonal. That's the most important part, okay? So with this, then we can start going to the physics. Look at the Schroedinger equation. How does a qubit evolve, right? So this is the so-called Schroedinger equation. It is actually very simple and easy if you write it in this bracket form. Can someone use English to tell me what is the meaning of this term? Partial psi, partial t. The rate of change of the state. Very good. The rate of change of state. That's it. How does it change? Well, it said that it changes if you multiply it by I times h bar, which are constants, is equal to itself times a matrix. And this matrix here, don't get confused, it's not Hadamard gate, it's the Hamiltonian. Okay? So-called Hamiltonian. And we also don't need to know what is Hamiltonian in this class. But it's not difficult to understand if someone tell you that Hamiltonian is the total energy of the system, which equals to the kinetic energy plus the potential energy. It's not surprising, right? How I change, how the particle change, of course depends on the energy landscape. Just imagine you have a roller coaster and then the cut is one of the particle. How the state is going to change really depends how the track lay out, right? You lay out in this way, like a parabola, maybe you will just keep oscillating like a parabola, back and forth. If you have 2 bumps, then maybe you can almost reach the highest one and then come back moving in this way, like this, right? So this is just a classical thinking, but just to tell you that if you know how the kinetic energy and potential energy will change as a function of position, then of course you should know how it will move. And that's why Hamiltonian, the total energy of this system, will determine its characteristic. And here is saying that if I have a qubit, due to certain Hamiltonian, maybe I shoot a laser pulse, a microwave pulse, that you inject energy to the system. Then it's going to change. How does it change? The change rate equals to the Hamiltonian times the state. That's it. Okay, so that's why you don't need to go deep, right? Now, we need to go deeper, and it is easy. What is psi, by the way? Now, in usually quantum mechanics scare us because of the wave function, right? A lot of complicated math tell me what is the probability of finding it at different point in the location. But in the bracket notation, particular for qubit, is so easy. Because what is psi? Psi is alpha 0 plus beta 1. This is what defines a state. I can also write it as alpha beta, as long as I know what the basis state is. The basis state doesn't change, right? So what is partial psi, partial t? It is just equal to partial alpha t, partial beta, partial t. You just multiply into the elements. Okay, so this equation is saying this. I h bar partial alpha partial t partial beta partial t equals to a matrix times alpha beta. So at this stage, you are just solving a system of linear equation. And your goal is to find alpha and beta. And once you know alpha and beta, of course, you know the state, because state is just alpha 0 plus beta 1, right? And that is Schroedinger equation, right? So easy, so simple. Right? Don't get confused, don't stress out when you heard about this equation. Particularly for qubit, it's very simple. It's just a 2 by 2 equation, 2 by 2 matrix. Okay, so if you want to design a quantum gate, we keep talking about Hadamard gate, NOT gate, whatever, then you see that you really depends on H. H is not the gate yet, but H is going to determine how alpha and beta is going to change. Then you wait for certain date, certain time, then it has a certain effect. But H is something that you will do to modify the qubit. And so you will shoot a correct laser pulse with the right energy, with the right amplitude, right phase, with the right frequency. Then your qubit is going to change based on this equation. Right? So in this class, we only look at two things. One is the Larmor precession to implement the Z gate, the phase shift gate, or arbitrary phase shift gate. And then the rapid oscillation to implement the, not really NOT gates, but go from the North Pole to South Pole. And we already learned that any gates can be combined by free rotation. So if I can rotate about Z gates, rotate about X gates, I just rotate a few more, then I can get any gate in that sense. Right? Just give you a simple feeling. The rest you need to go to E274. Right? Now, so that's why H is important. So H, okay, you can implement it in this way. This is a general way. You can do this. This is a general. If I have n qubits, okay, if I have n qubits, for each of the qubits, I can have one Hamiltonian. Okay, the whole system. Each of them, I add some laser pulse, but you also need to do 2 qubit gates so that they can interact with each other. Okay, but you will do like, in order not to repeat, we'll just do I smaller than j. Okay, so Hi is the single qubit. I say it wrong again, right? This is not a gate, but it is going to create a gate. Okay, so it affects Q bit I. And usually we will do this. We say this is HA I sigma A I. Okay, so what do you do is this. You apply the Hamiltonian, you will use the Pauli matrix, right? This is the easiest one. And you only turn it for a certain time. This is HAI. Right? You cannot keep applying the ZK, otherwise keep rotating, right? So you just apply for a certain time. So this is a step function, okay, with a certain width. For Hij, the 2 cubic gates, we won't discuss here, and it is very difficult. And in principle, this is an active research area, right? How to add as control 2 qubit, particularly for entanglement gates with high fidelity. But in general, you can say this is like UAB, which is again a scalar, right? You go between 2 qubits, and then you do something so that they are related, but each of them is like they are getting a sigma B, a sigma matrix, I mean a Pauli matrix, okay? But we won't go into detail for this, but just for completeness, I show that in general you can decompose into this. Of course, you can also have 3 cubic gates, 4 cubic gates, but it's difficult to implement. So usually people don't do that. Okay, so this is the general Hamiltonian, right? So now, from now on, we are going to look at only the single cubic gates. Okay, so I still have time. Then let's look at how the qubit is going to evolve. Let's go through some math. I think I will start from here because of space. Let me write down the equation again. Maybe to save space, I won't write it. Let me just say, let's say we have n equal to 2, which means what? Actually, this n is not this n. Let me just say 1 instead of 2. 1 qubit. Okay, so you have basis state, you have 0 and 1 as the basis states. Okay, so then I write psi equals to alpha 0 plus beta 1. I'm repeating. Then we have what? We have partial psi partial t equals to partial alpha 0. Partial alpha partial t 0 plus partial beta partial t 1. Is this okay? This is just the same as what I wrote earlier. Partial alpha partial t partial beta partial t. Right? I just write it in brackets, so you need to indicate 0 and 1. Here is column. I know this is 0, this is 1. This one, right? So I'm going to do this. I'm going to apply not yet. I need to write the equation. So with this, then I'm going to write the equation. I'm a little bit too fast. Partial I, write the Schroedinger equation. I'm writing partial psi which is alpha partial t 0 plus partial beta partial t 1 equals to h times alpha 0 plus beta 1 What I'm doing here is I just use Schrodinger, maybe I should write here. Earlier I showed you the Schrodinger equation is I h bar psi equals to, no, partial psi, partial t equal to h psi, right? Remember? The rates of change of the state proportional to h times psi. So now I have IH bar. I substitute the psi, which is alpha 0 plus beta 1. So that's why I just write partial alpha, partial t 0 plus partial beta, partial t 1. The other side, I just write it as it is, right? Because h times psi, so h times is alpha and beta, right? So I'm going to do this. That's why Dirac equation becomes very useful. I'm going to apply a state k on the left to it. K can be 0 or 1, just general. I just want to do a general state. Multiply k from the left. What does it mean? This becomes I h bar partial alpha partial t k zero plus partial beta partial t k one on the left hand side. On the right hand side, it becomes h alpha k 0 plus beta k 1. What I'm doing is just do an inner product to both sides. That's what I'm doing. And when you do inner products, these are just scalar, right? I can do the product directly to 0 and 1, 0 and 1. Is that okay? Now, if k equals to 0, what do you get? The 1 will be gone, right? Because they're orthonormal. Then this one I get is y h bar partial alpha partial t. 0 in the product 0 is what? 1. Very good. Equals to h alpha. H alpha. Right? Because this term is gone. 0 in the product 1 is gone. 0 in product 1 is gone. 0 in the product 0 in the product is 1. I have this equation. Similarly, if k equals to 1, then I have I h bar times partial beta partial t equals to h beta. Okay, and then we will form the equation. Yeah, I think I say something wrong, right? Yeah, say it. Yeah, so I did something wrong, right? Thank you very much. I did a very big mistake, right? Do you guys understand what he mean? Here, can I go from here to here directly? No, because I need to put on the left of h. H is the Hamiltonian, so I'm a little bit rushed and give you all the wrong stuff. So let me rewrite it, and that's why the result I got was wrong. Sorry for that. So this needs to be k h and then the whole thing for alpha 0 plus beta 1. Make sense? Do you see what I make what mistake I make, right? Because this is H is not a number. It should go, I cannot go into H. Okay? And because of this, then this part is also wrong. And that's why my result is wrong. This part should be, if it is 0, it becomes 0, H, 0 times alpha plus beta times 0, H1. Okay? And similarly for this one, when it is 1, it becomes alpha 1, H0, and then plus beta 1, H1. Correct now? Makes sense? Okay, so sorry for confusing you. So I will continue next class. Okay.